Hello students, welcome back. Let's go back to section 4. Previously we studied linear, quadratic, and power functions, these three. Now the next topic is polynomial functions, and here we go. What is a polynomial? It's a function defined like this. Now this n value, that's going to be any whole number, that is 0, 1, 2, 3, 4, 5, 6, and so on. If n is 0, then all these are out, and we have just a0, a constant function. If n is 1, then we don't have any of these, so what's left is just a linear function. If n is 2, then we don't have any of those, and we have a quadratic function, and so on. So polynomial is a bit broader. Let's take care of some lingos. These things are called terms. Nth term, or the leading term. The leading term, because in the descending order, highest degree first, and the next highest degree, and the next highest degree, in that order, the highest degree comes first, so typically we call it the leading term. And the last one here is called the constant term. There's no x in there, so it's constant. Otherwise, we have this one, linear term, first degree term, quadratic term, second degree term, cubic term, the third degree term, and then quartic, and then quintic, and so on. Those are terms. Now terms, each term consists of a number part and x to the whatever part. The number part is called coefficient. a1, a2, a3, all the way up to an, those are called coefficient. Likewise, we have an leading coefficient, and then a1, for example, is linear coefficient, and then quadratic coefficient, cubic coefficient, and so on. And there's a bit of a confusion here. How about a0? Is it considered as a coefficient, or there's no x in there, so it's not a coefficient? Well, there's confusion even among mathematicians, actually. People do not agree. Some people call a0 as a constant coefficient, as in a0 x to the 0 power, which is just 1. But some people do not call it coefficient because there's no x in there. Me personally, I'd like to consider it as a coefficient. And as for our textbook author, our textbook does not consider a0 as a coefficient. But those are just lingos, not that important. Something to remember, the degree of a polynomial, or some people call it order, and the n value, the biggest n value, that's basically it. And of course, for that, the coefficient should not be 0. If this is 0, then that's 0, so everything just drops out and we go to the next. And if all those are 0, then we go only constant function. In that case, the degree is 0. The domain of a polynomial is always negative infinity to positive infinity because polynomial is defined only by repeated multiplication and repeated addition. No division, so you don't have to worry about dividing by 0 or things like those. How about the range? Well, the range is some minimum for positive infinity, like this, if you have even degree with positive leading coefficient. Or the other way around, we have maximum, negative infinity to maximum, for even degree and negative leading coefficient. But if you have odd degree, then range is negative infinity to positive infinity. Either way, this way, that way, go on forever. Those are the basics. Next topic, asymptotic equivalence and end behavior. This too should be familiar to everybody, even though you may not be completely comfortable with the notation. The idea is this. The end behavior is determined by the leading term only. Everything else is just secondary, so you can just cross those out. And a good way to represent the same idea is to define a new function given only by the leading term, call it g, and these two functions, f and g, are asymptotically equivalent as x gets really positive or really negative. Asymptotically equivalent, what do you mean by that? The definition is kind of like this, using the limit, but that's a little bit difficult to understand. So here we have some graphical explanation. We have a general polynomial function and g of x given by its leading term only. When the x value is rather small, then you can see a significant difference between the two. This is intermediate stage, and when x is really big, then you don't see much difference between the two, right? That's a visualization of asymptotic equivalence. It turns out that the ratio f of x over g of x gets very close to 1 if x gets really large. That does not mean f of x and g of x gets pretty close to each other. I mean, this does not mean and this thing these two are different. So this one is actually stronger. The difference is getting closer to 0 versus the ratio is getting close to 1. If they're the same, then of course the ratio is 1, then difference is 0. But they are getting close to each other, that's very different as a matter of fact. We'll talk a little bit more about getting closer and closer concept and this limit expression starting from next week. For now, graphical understanding will do. By the way, there goes one example. Here goes another example. Again, you can see big difference between the two functions. They're not the same, but asymptotically they are equivalent. So, the end behavior is determined by the leading term only. So, whether the graph is, roughly speaking, kind of U-shaped so that we have minimum and then toward positive infinity or negative infinity, either way going to infinity, or the other way around, we have a maximum, or neither maximum nor minimum, have a range of negative infinity to positive infinity. All those kind of end behavior, all those are determined by the leading term only. That's because of this asymptotic equivalence. Let's not worry too much about local equivalence yet. And let's just go over to rational functions. Because with polynomial functions, it's difficult to visualize that asymptotic equivalence. I showed you some picture, but that's a bit limited. Rational functions are defined as polynomial over polynomial. Just like rational number is defined by integer over integer. Of course, denominator is non-zero. You cannot divide by 0. So that means we have some domain issues to consider. And rational functions often come with asymptotes. Horizontal asymptote, vertical asymptotes, slanted asymptote, or curved asymptote. Horizontal asymptote and also, horizontal asymptote. That's the only one that you can explain toward the asymptotic equivalence. Slanted asymptote and curved asymptote, yes, to a certain degree we can explain, but something more sophisticated is necessary to get more precise result. But horizontal asymptote, we can visualize through asymptotic equivalence only. Kind of like this, you see. Take the leading term only for the numerator. Take the leading term only for the denominator. Basically, we are taking the asymptotic equivalence for the numerator and denominator. And what do you end up with? We end up with a monomial, a power function. And we know an awful lot about power function. Whether that behaves, blowing up to infinity or stay constant or going down to zero, those kind of things. Here's a visualization. So we have this function, but we take the asymptotic equivalence, throw away the unimportant terms, and take highest degree terms only, and simplify. We have 5 seconds, 5 halves. And what do you have? We have a constant. So when x value is small, looks like there's a significant difference. But when x value is large, you clearly see horizontal asymptotic behavior. So asymptotic equivalence is quite useful calculating out horizontal asymptotes. Here's another example. This time denominator has higher degree. You take the asymptotic equivalence anyway, and then 2x squared over 4x to the 4th power. Simplify further, we have 1 over 2x squared, and that goes down to 0. Again, asymptotic equivalence. And fair warning, f of x, blue, and g of x, red, and constant 0, green, they're 3 different functions. They're not the same, but they're all asymptotically equivalent when x value is humongous. Humongously positive or humongously negative. You see, when x is small, they're all different. Look at the second picture. When x is large, to the right or to the left, humongously positive or humongously negative, they're equivalent. And that's what we're looking at. And that's how you get horizontal asymptote. When the numerator has higher degree, then no horizontal asymptote. Let's see. Yeah, there goes an explanation about slanted asymptote or oblique asymptote when the numerator has 1 higher degree. By taking the asymptotic equivalence, you get a linear function. So the horizontal asymptote, no horizontal asymptote, slanted asymptote must have a slope of 2/3. But this line itself is not a slanted asymptote. They share a similar asymptotic behavior, the same slope, yes, but they don't get closer and closer and closer together. It turns out you have to do something more. You have to do some polynomial division and do something, and then you get real slanted asymptote. But please note that the slope is the same as the one you got before through this asymptotic equivalence behavior. This kind of computation is not something we are interested in for this course. The asymptotic equivalence, that one is. Here's another example, this time curved asymptote example. If you simply take the leading terms, and simplify, we have 2x squared, quadratic function, and compare those in small x values, they're different. But in large x values, they behave kind of similarly. I don't say they are getting closer and closer and closer together. As you can see, it looks like there is a difference. Still, they show same end behavior and asymptotically equivalent. Simple computation yields the end behavior, and that is sufficient. If you really want to find out this asymptote itself, you have to do a little bit more sophisticated computation, polynomial division and taking the quotient. And if you do that, then you indeed get this curved asymptote like this. Even for small x values, you can see this asymptotic behavior there. And for large x values, you can clearly see this is a curved asymptote. Again, we are not really interested in finding out these asymptotes. We are interested in only the end behavior and asymptotic equivalence. Just taking the highest degree term and crossing out the rest. Remember that trick because we are going to be using that over and over again in this course.